Okay, go ahead and flip open in your packets to page number 37. We're going to do the warm-up and the launch for task 2.6 today. All right, let's zoom in and see what it's asking for here in this little quick warm-up. So it's asking me to look at these expressions, these equations, and see if they are quadratic. And the definition of quadratic is that it has a power of 2, an x squared. So you guys see that if I multiplied this together, we would get 6x squared minus 11x. So we would say, yes, it's quadratic because it is the product of x times x, which equals x squared. Looking at the next one, this has a 6x squared, this has a 6x squared, but technically, if I subtracted those out from both sides, do you see that it would cancel? And it would just leave me x equals negative 11. So this is not quadratic because the x squared cancels out. How about the last one? You got it. Yes, it's quadratic because it has an x squared. Okay, now let's look at some tables here. Yay, table work, our favorite. Identify if the table represents a linear or a quadratic, and then write the recursive for each. All right, so zooming in here. From a 3 to a 12, 12 minus 3, do you see that's a plus 9? 27 minus 12, it's plus 15. 48 minus 27, and 75 minus 48. Okay, finding the constant second difference if there is one. Oh, look, do you see that plus 6 showing up? So the type of function is quadratic because of that constant second difference. And then the recursive goes f of 1 equals 3, f of x equals f of x minus 1, and we need to go get that linear rate of change recursive piece. So pick a row, any row, and I go begins with 27, adding 6 each time to the one before 5. So 27 minus 30 is going to give us minus 3. So there's my recursive piece. Okay. Next one goes from a 7 to a 10. So this one is linear. So f of 1 equals 7. F of x equals f of x minus 1 plus 3. So linears have a constant first difference, and quadratics have a linear first difference, in case you were wondering. Okay, now we're on the actual task, and it's having us do a quick jump start. Find all the pairs of factors for each of the following. So just to sort of remember what a factor is. For example, for 42, I could say 1 times 42, 2 times 21, 3 times 14, 4 doesn't go in, 5 doesn't go in, 6 times 7, 8 doesn't go in, and 9 doesn't go in. So you're double checking all the pairs like 1, 2, 3, 4, 5. Does it divide in? This is a 2 times 21. Okay, let's try 54 now. 1 times 54. 2 times 27. 3 times 18. Double check me on that one. 4 times, doesn't go in. 5 doesn't go in. 6 times 9. 7 doesn't go in. 8 doesn't go in. And there we go. There's our list of factors. 72 would be 1 times 72. 2 times 36. 3 goes in once. So 24. 3 times 24. 4 times 18. 5 doesn't go in. 6 times 12. 7 doesn't go in. 8 times 9. So there's all my lists of factors for 72. 1 times 110. 2 times 55. 3 doesn't go in. 4 doesn't go in. 5 goes in. 22 times. 6 doesn't go in. 7 doesn't go in. 8 doesn't go in. 9 doesn't go in. So we're already done with 1 times 110, 5 times 22, 2 times 55. Okay, going over those factors, the pairs of factors, is going to help us on this upcoming lesson. So Optima Prime has a quilt shop that makes and sells squares of fabric for quilting. At first, her quilts only made square blocks for quilters. Then Optima spent her time making perfect squares. Customer service reps were trained to ask for the length of the side that was being ordered. They would let the customer know the area of the block to be quilted. Optima found that many customers came to the store making designs that required a combination of squares and rectangles. So Optima's Quilt decided to produce several new lines of rectangular quilt blocks. Each new line is described in terms of the rectangular block that has been modified from the original square block. So example, one line of quilt blocks consisting starting with a square block and extended by 5 and the other side by 2 would show up as this equation. So side length extended by 5, the other side length extended by 2. So the design department knows that the area of this new block can be represented by this equation, but they don't feel this equation gives a real sense of how much bigger the new block is or how much area when compared to the original. So, can you find a different expression to represent the area of the new rectangular block? Need to convince the customers using a diagram. So we've got this original square, and one side length is extended by, let's go back and remind us, by 5 and then by 2. So this side is extended by 5. This side is extended by 2. 1, 2, 3, 4, 5, 6, 7 x's. And then the little individuals. So we get x squared plus 7x plus 10 little squares. And you would represent this showing the customer that there's the x squared, there's the 7x's, And there's the plus 10 little constants at the end. Here are some additional little lines of blocks that they've introduced. Find 2 different algebraic expressions for each. So you guys are just going to spend today drawing out your basic block, extending by how much on one side, and extending by how much more on the other. This is my x extended by 3 side, my x extended by 4, and then my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So expression number 1 is using these outside labels here and here. And then expression 2 is reading off these interior ones, x squared plus 7x plus 10. And we can see that here. Here's my 7x's. And here's my plus 10. Extended by 4 inches only on one side. Only on one side. So this time we've got x by x plus 4. Here's my side labels over here. Then you've got your x squared plus 4x's and there's our 2 expressions. The original block extended by 5 inches on either side. That's the x plus 5 squared perfect. And that gives us x squared plus 10x plus 25. And we can see the x squared right here, the 10x's right there, and the 25 little squares right there. The original square extended by 2 on one side and 6 on the other. So my first expression is the x plus 2, x plus 6. And remember that that comes from these little labels on the side. And then my full expression is x squared plus 8x plus 12. I see the x squared right there, the 6, 7, 8 x's, and the 12 little squares there. So we're seeing a square up here. We're seeing a rectangle down there. We're getting good at these diagrams. Okay, customer service needs to have specific instructions on how to make the new design for the manufacturing team. And the instructions need to explain how they extend the sides on a square block to create the new line. The customer service department has placed the following orders on your desk. For each, describe how you can make the new blocks by extending. Your instructions should include diagrams and algebraic descriptions. So we've got the square block on one side extended by 5, and on the other side extended by 3. So here's my extended by 5, here's my extended by 3. Pause the video and go try these other ones, and then let's check to see how you did. $18. These two come from here and here, and the equivalent expression comes from there. Okay. Are you getting good at these diagrams yet? Okay, looking over here at page 42, we're saying forget the stinking diagrams now. Can we just come up with this expression being given the other one? This, my dear friends, is a big deal topic of Math 2 called factoring. So we're going to take each of these. I also call it the product sum game. Where we're saying what times what is going to give me this. So see how we need an x squared at the front? So x times x. We need a 10 at the end. Think of two factors that make 10. Well, I could think of 2 and 5, but those don't add up to the 11 in the middle. So what other factors can you think of that make the 11 in the middle? What else times what else equals 10? You got it. It's the x extended by 1, x extended by 10. There's my factors. Now this next one also wants 10 again, but this time the middle term is 7. There's my 2 and my 5, because those add up to 7. What times what makes 8 and adds up to 9? 8 times 1 is 8 and adds up to the middle term of 9. What times what is 8 and adds up to 6? 4 and 2. 4 times 2 makes 8. 4 plus 2 makes 6. What times what equals 12 and adds up to 8? You got it. 6 times 2 makes 12, and 6 plus 2 equals 8. What times what multiplies to give me 12 and adds up to 7? 4 times 3 is 12, and 4 plus 3 is 7. What times what adds up to 12, multiplies to 12 and adds up to 13? There's my 1 times 12 makes 12, and 1 plus 12 equals 13. What relationships or patterns do you notice to find the sides of the rectangles? So given any m and n lengths, we multiply m times n to get the end value and add m plus n to get the middle. So I like to call this the product and the sum. A customer asked for a rectangle with x squared plus 7x plus 9. The customer service representative said the shop couldn't make that rectangle. Do you agree or disagree? How can you tell if a rectangle can be constructed from the given area? Let's think of all the possible factors for 9. There could be 1 times 9, there could be 3 times 3. Those are my only options. Does the 1 times 9 give me 9? Yes. But does 1 plus 9 equal 7? No. Does the 3 times 3 give me 9? Yes. Does 3 plus 3 give me 7? No. So there's no possible way to factor this because there's no factors of 9 as a product that would give us 7 as a sum. Okay, here's some crazy ready for mores. Pause the video for a second and see if you can do these really difficult ones. Remember to make a list of factors if possible. Okay, let's see how you did. 42 could be 3 times 14, and that adds up to 17. 54 could be 3 times 18, and that adds up to 21. 27 could be 3 times 24, and that adds up to 27. 110 could be 22 times 5. All of these were part of the factor pairs that we did way back at the beginning in the warm-up. So if you look back at those factor pairs, you'll see these options. Those ones were kind of like a bonus at the end, not necessary, just for fun.